All right. Hello, hello, hello. This video is going to be going over temperature conversions, looking at converting back and forth between them. I'm also going to give you a few notes about temperature scales uh, so that you have that information as well. First thing I want to mention though, this is a mistake. This should say worksheet 6.3 and topic 6.3 in Canvas is where you're going to find this worksheet and later the key. So first off, notes. Okay, Fahrenheit scale and centigrade scale, the two in the middle here. That's how you spell those, by the way. Celsius. Centigrade is CENTI grade, GRADE. Okay, centigrade, like centimeter, but grade. Okay, these two scales were designed to be used. Okay, when these two scales were being designed, the intent was that they be useful for people. So the way these scales were built was we assigned a 0 point, we assigned a 100-degree mark, and then we moved forward with life. Okay, everything between those is going to be your degrees. So Fahrenheit scale came along first. When they designed this scale, they set 0 to be the temperature at which brine, or salt water, freezes. Okay? Brine freezes at 0 degrees centigrade. That, Fahrenheit, 0 degrees Fahrenheit, is where brine freezes. Brine is spelled B-R-I-N-E. Okay? 100 degrees Fahrenheit was intended to be the temperature of the human body. And it was the temperature of the human body at the time. Put a pin in that. We'll come back to that in a bit. Okay, then between the temperature at which brine freezes and the temperature of a healthy human body, we take that amount of energy, those two, divide that into 100 even sections, and then extend that amount infinitely in both directions. Well, infinitely in this direction, not quite so infinitely as we go down, which we'll talk about later. And we have the Fahrenheit scale. Same basic idea with Celsius, but this time the Fahrenheit scale was built around sustainability. That you can survive in temperatures between 0 Fahrenheit and 100 Fahrenheit. That's basically, it's designed around life. If it gets much hotter than 100, it's unsafe to be outside, because at that point, thermal energy flows into your body instead of out. You get sick and you die. That's why there's heat advisories when the temperature goes over 100 degrees. It's unsafe to be outside at that point. Same with below 32. If it's cold enough that even the salt water is freezing, the oceans are starting to freeze, it's not safe to be outside. Okay? Celsius, though, or centigrade, was designed specifically around fresh water. So 0 for Celsius is the temperature at which fresh water freezes, while 100 degrees is the temperature where fresh water boils. Okay? Now that is a much, much wider range than the Fahrenheit scale. So as a result of that, 1 degree, an increase of 1 degree centigrade, is a lot more than an increase of 1 degree Fahrenheit. I think it's 70-ish Fahrenheit is around 36 Celsius, I think. So there's a big difference in these two temperature scales. Now, that said, these two were designed around life. Okay? Intended to be used by common people, by normal people in their day-to-day lives. What temperature is it? Well, it's 70 degrees Fahrenheit. It's 30 degrees Celsius. Okay? People who are used to those systems know what that means. However, when we started trying to do thermodynamic calculations using either of these scales, it was really difficult. Because, remember, temperature tracks the amount of thermal energy. I forgot to go back and do something. Before we get into this, I mentioned that 100 on the Fahrenheit scale was the temperature of the human body. These two scales were not designed with each other in mind. And it was actually impossible to convert back and forth between these. So, as a result, what was done, the centigrade scale was more widely accepted throughout the world, kind of like the metric system is much more widely accepted throughout the world at this point. And so, an agreement was made to change the amount of 1 degree Fahrenheit. We made it just a little bit less. And by making that small change, it is now relatively easy to convert between Celsius and Fahrenheit, because 1 degree Fahrenheit is exactly 5/9 of 1 degree Celsius. It used to be an irrational number. Okay? There was no convenient conversion. You couldn't represent it conveniently as a fraction. It was an insanely long decimal to try to convert here, which meant you were always rounding. Now you're not. Now, as a result of changing Fahrenheit, reducing that by just a little bit to make that true, Fahrenheit's 100 is no longer the temperature of the human body. Okay, the temperature of the human body is now just a little less than 100 Fahrenheit because we reduced how much a Fahrenheit is. So, as a result, we can now convert easily between these, but that's why that discrepancy exists. Okay, the same thing was done, by the way, with an inch. Okay, 1 centimeter, or converting back and forth between English and metric lengths, had the same problem for a while. It was basically impossible to do it accurately. And so we adjusted the length of an inch. And I don't remember whether we made it bigger or smaller. I just know that we changed it. We changed it, and this is why there are now exactly 2.54 centimeters in 1 inch. It is a perfect conversion rate. This is also why, if you try to work on an old car with new tools, you cannot get a perfect fit with any of your wrenches, because all those bolts are in there using the old English system, while your wrenches are using the new English system. And an inch is different in those two systems. And now that I've gone on that tangent, let's get back to this. Okay, thermal energy is, or temperature is tracking thermal energy, and in physics, the fact that that can sometimes be a negative number is a real problem, because temperature can be a negative number. Celsius and Fahrenheit both go into the negatives. That's a problem when you're trying to account for thermal energy, because you can't have a negative amount of energy. It's not possible to have negative energy. That's not a thing. So, a new scale was devised, the Kelvin scale. Okay? There is this concept, this idea. It's called absolute zero. Absolute zero is the temperature, and this is a vocab word, you have to know this. Absolute zero is the temperature at which there is zero thermal energy present. Okay, no vibrational energy remains. It's all gone. We call that absolute zero. By the way, space is about 2 to 4 degrees, depending on who you ask, above absolute zero. Kelvin scale is set up so that 0 on the Kelvin scale is absolute zero. So there is no negative number on the Kelvin scale. There's no negative degrees. It has to be positive or 0. The Rankine scale is the same thing, except that Kelvin was designed using degrees centigrade. So a change in temperature of 1 degree Celsius is a change in temperature of 1 degree Kelvin. They are linear. Okay? Now this number is going to be very different, but let's say you go from 0 degrees Celsius to 1 degree Celsius. Temperature has gone up by 1. You will go up by 1 in Kelvin as well. You will go from 273 Kelvin to 274 Kelvin. The degrees are the same. The change is the same. But this number can be negative, while this one cannot. The same thing was done for Rankine using Fahrenheit. Okay, and because 1 degree Fahrenheit is less, it takes a lot more Fahrenheit to equal that Rankine. So negative 273 Celsius is 0 Kelvin. Negative 459 is 0 Rankine. Now, actually, that's pretty much it for the notes. I'm going to end this here because this video is close to 11 minutes, and I'll upload this and then the actual work separate. So I'll be back in a minute with the video going through the actual calculations.